Stanford University.
My name is Yi Chui. I'm from Material Science Department right here at Stanford University. Today is about batteries, tutorials. So it will be different from the regular research talk you listen before. This is the chance you can ask any questions you like. We'll go slowly and try to get you started. Maybe you forget about what battery is since undergraduate. Now here's a good chance to refresh your memory and try to see what are the fundamental principles guiding the battery research, where the technology breakthrough might come from. As I said, you are welcome to ask anything you would like to ask during the talk. It's supposed to be highly interactive. So the importance of batteries, the way I learned about batteries is important, mainly coming from portable electronics first. You know, how often I need to recharge my iPhone and laptops. These gadgets really give you the impression, you know, how important the battery is. Certainly, we know the cars having the lead-acid battery right there for a long time now. It's a battery used for starting up your car and also supporting the electricity during the running of the car. And my impression on the battery technology becomes even more after I have kids. They have a lot of toys, right? I just need to change batteries so often that actually this really motivates me a lot more than portable electronics. Surprisingly, you know, the frequency of changing the batteries in the toys is a lot more than you know, the inconvenience to charge up your cell phone and laptops. So the emerging market is the car electrification and the hybrid and the plug-in and the all-electrical vehicles. All this market combined is probably only 1% of this market. This is a lot bigger. There's a lot of great potential in the battery research. If you look down the road, solar and wind, all these renewables combining with grids, this require a lot more batteries, much higher energy storage. The scale is much bigger than a car. And how exactly you do it is still questioned. So overall, energy storage now already have pretty big market. We have a baseline technology. But to move one step further, we don't really have a great solution yet. I hope after today's talk, you understand, you know, how batteries work, where the technology breakthrough might come from. You can understand a lot more what's going on in the world. Now let's look at the basic parameters you really like for an energy storage. I put different technologies right here. Battery is sitting in a position in terms of how much energy you can store and how much power you can output compared to other technology. And batteries compared to fuel cells that's using the chemical fuel is lower and how much energy, but the power is usually better. Now let's define this parameter a little bit. One key parameter is how much energy you store per unit weight or volume. Let's define the terminology. Energy density is energy you can store per unit volume. Specific energy is the energy you store per unit weight. But people interchange these two terms so often. Oftentimes they talk about energy density, they really mean either of this or both of this. So you just need to understand people swap this terminology so frequently. And now power is different, a different thing. If you are not an engineer, you are an investor, for example, power and energy means different things. Power is how fast you get the energy out. If you use it for the car, energy density means, you know, how far you can go per charge of your batteries. Power is how fast you can get your car to speed up. Cycle life, we talk about charge, discharge. And cycle life also define the value of the battery to a great extent. Calendar life is important. Don't overlook the calendar life. If you buy a new battery, you don't use it, you just let it sit. After 3 years, it's probably already bad, even though you don't use it at all. So calendar life is very important. Just internal chemistry keep going on, even though you don't use the batteries. Safety, this become more and more important. And going from a portable electronics, you have a couple of those cylinder cells packed into your cell phone and laptop, to a car batteries, electrical vehicles, you have 7,000 batteries in the Tesla's car. That's very different challenge in solving the safety problem. In the case of electrical vehicles, if you have one bad battery, you don't control it well, it blow up, the 7,000 battery will come together, so that's a big explosion compared to portable electronics. The cost is also important. It's usually measured, giving certain amount of energy you can store, how much you need to pay. We will get to that a little bit later. Now looking at these different desire parameters, let's come back to these applications. Let me ask you, what do you think, which parameter is important for certain applications? These parameters is highly application dependent. You emphasize one more than the other. If I ask you, for portable electronics, what do you care the most? What really stand out as the most important thing you care? Anyone giving me a, okay. Energy density, cycle life. Okay, we have two opinions right here. Any others? Cost, okay. So now let's see, looking at the current technology, right? If you buy a battery, let's say for the iPhone, it's most likely only costs about $5. If it's $15, you probably don't care, right? It's just $300, $400, $15. This ratio is small. But if you can get your battery to be used for much longer time per charge, I think you probably will be happy to buy it. I will be happy to buy it. Energy density is very important right here, how much you can store. And cycle life. For portable electronics, let's say, for the young guys, probably use a year or 2 or 3 years most, and then you change to something else, right? And then your battery needs to change too. So what you need is 3 years, roughly 300 cycles. That's the cycle life. That's good enough. Probably at most 500 cycles if you use it too often. The current technology can really satisfy that. But it's the energy density that stands out the most. Now let's look at electrical vehicles. What do you like to have right there? What stands out the most? Power density.
And energy, but also power.
Okay, energy and power. Which one is more important?
Depends which car I have. If it's a Tesla, it's power density.
You want to drive fast? Okay.
Energy density is more important.
Yeah, energy density. So energy density relates to range. Power density relates how fast you can accelerate. Lifetime. Okay, yeah, lifetime. Any other different opinion? Safety. Okay. These are all good. Now let's look at the electrical vehicles. So Tesla uses about 7,000 batteries. In reality, in the usual car, you cannot pack so many batteries inside this. This car has an engine and a batteries. No other things as a big component. So actually, the energy density we have is not enough. The battery power to accelerate a car, depending on how fast you do it, if you are looking for 3.9 seconds, you do need a lot of power. For the usual driving habit, the battery power is actually sufficient. And the next key thing is actually safety, because you have so many batteries right there. Safety is a big concern. This one opinion on the calendar life, on the lifetime. That's important too. But this learning curve more and more looks like we are getting there, slowly getting there. So 5 years, we probably can get there. 10 years is uncertain at this moment. We might not get there. 10 years is really what you like to have. The most fundamental parameter right here is energy density. But that doesn't mean other parameters are not important. In a couple of years, this parameter's priority will change too once you learn something about the battery for the car. Now for here, what's important? This super large scale energy storage. Cycle life, okay? Cost, great. Actually, cost is stand out the most. And because we have no way to envision how we get there in cost, we are still probably 5 times too expensive. And we are already in a very aggressive cost learning curve. And the cost is cut down by a lot. How do we get there? Cost stand out as the most important parameters. So now you see, depending on what the application is, these parameters stand out the most. And this comes back to the technology, the materials and technology. And you will need to think about different strategies to tackle different application problems. Now let's come back to the basic battery cells. What's so special about batteries? We know a simple chemical reaction. You put A chemicals and B together, they react. If B would like to get electrons, A would like to lose electrons, they form AB. You get the energy out. That's called a free energy delta G right here. In the regular chemical reaction, A and B put together, and they release energy. How do they do it? Usually they become heat, right? You lose the energy right away. So put A and B in contact, slowly they react, produce AB. At the end, you consume all the A and B. Electrochemical cell is about how do you really take that electrons out. We notice electron going from A to B and forming a bonding. And this process is energy production process. Can you bypass this direct electron transfer going from A to B? You design something like this. A lose electron, produce A plus, become an ion. You take these electrons out and go to the outside circuit and give it to B, and then let the A and B combine. And this way, you really separate the two processes, separate the whole reaction into a half reaction. That's an electrochemical cell. You separate A and B, don't let them in contact, but you connect them through an electronic path. And this way, you have iPhone right here, the devices you like to power. A lose electron, it goes out, but A become A plus, diffuse through this electrolyte, go to the B and produce AB. Eventually, the whole reaction finished completely. So adding the electrolyte is a very important component to realize electrochemical cells. At the end, it's this delta G, the free energy now, converted into the electricity. That's delta G determining the voltage E of your batteries. F is a Faraday constant, N is the moles of electrons you get out during this process. Very straightforward, a simple way to use the chemical energy to do the work. Now, from this and the outside, why battery is so important is really due to its energy efficiency on one hand. We know this, based on this, the amount of work you can do is really the free energy you have from this chemical reaction. You write it from thermodynamics, very simple one, related to delta G enthalpy and an entropy term. You look at a heat engine, let's use the Carnot efficiency. The amount of work you can do related to how high the temperature you go to, the hot side and the cool side, and the fraction of the enthalpy can be extracted out to do work. At the end, you compare this. Let's use a simple lead-acid batteries. You put in all these parameters, free energy, enthalpy, and entropy. You compare, assuming the hot side is 600 Kelvin, a cold side is 300. You get it right away. The amount of work you can do using a battery idea is 3 times more than a heat engine. At the end, you're talking about energy efficiency, roughly this number. I mean, this variation depending on what battery you use and what engine you use. Roughly, it's a 3 times difference. So that's very attractive to take out the energy from a chemical reaction through an electrochemical method. Energy efficiency is very high. So basic requirement now let's come to the real part. That's really the guiding principle, the real part. How do you really get battery to work? You need A to move, become an ion, go to B and produce AB. First of all, to generate a voltage, you would like to have A and B. They have different affinity to the electrons. One like electron more than the other. Once there's a difference, you will be able to generate a voltage. And AB should be electronically conducting, because you need to take electrons out from inside here to the outside. A and B, they need to be electronically conducting. It turned out this is one of the challenges for a lot of materials. A lot of materials are not conducting enough. You need to find a solution to make them conducting. The electrolyte needs to be electronically insulating. You don't want electrons go from A to B through the electrolyte directly. This will be leakage current right there. You do not want that. That consumes your energy. But you want them to be ionically conducting, so ions can move. If it's a solution, making it ionically conducting is usually easy. But if this electrolyte is solid, it's a completely different story. Actually, there's a lot of technology innovation in that area. How do you really get solid electrolyte conducting enough? You can produce enough ion flux, produce enough power. At the end, you need the electrons move fast. Ions also move fast enough to produce high power. You also like to have is A do not react with electrolyte, B do not react with electrolyte. If A and electrolyte react, instead of A diffuse to the B and react, you have a side chemical reaction in the electrolyte. The battery is dead very fast. So these also are very important guiding principles, how you design the battery, design your materials. For rechargeable battery, you need this reaction to be reversible. A and B becomes AB. AB can come back to produce A and B. That's also very important for the most application we care. That's all rechargeable batteries. We start saying is, a battery you can do it in a way extremely low tech, right? You don't really need much to make a batteries. You need 2 electrodes. They have different affinity with electrons. And then you need an electrolyte. This can be as simple as fruit, the juice you have. This is enough electrolyte inside. If you put this is zinc, this is copper, and connect this together, you can power a light bulb pretty easily. So if the power ever goes out in your house, you have some fruit in your house, right? This will be the idea you can think about to light up your house. It's not a bad idea. Now let's compare a little bit, different energy storage mechanisms. What's the difference between battery and capacitors and supercapacitors or ultracapacitors? Now let's look at this in a little bit. You can appreciate a little bit more about why batteries is important. We know in a capacitor in high school physics, right, you have 2 parallel plates, put them together in a very close distance with a dielectric, an insulating layer right there. You apply a voltage, you can store charge as a capacitor. The amount of energy you store is related to the capacitance of this capacitor. And the voltage you apply goes to the square. And this is 2 parallel plates, very simple. The capacitance is related to the bigger the areas you have in close to proximity, and also related to the thickness. You want this distance to be small. But in realistic, get down below 1 micron. It's hard unless you use advanced semiconductor fabrication. to do it. And below that, it's very easy to get leakage. The amount of energy you can store is limited. Now you look at ultracapacitors. Ultracapacitor is an idea to change these solid-state dielectrics to electrolyte solution. You have a phenomenon called electrical double layer. Now you apply a voltage, positive this side, negative this side, you accumulate negative charge in solution right here. You're forming so-called a double layer. Now the separation between the positive and negative charge is so close, it's in the order of a nanometer also. So you reduce this distance by roughly 1,000 times. Your capacitance goes up dramatically by 1,000 times. Now, in reality, this is two capacitors connected in series. You can calculate right away. The amount of energy you store in an ultracapacitor is so much higher than a regular capacitor. Question?
Why is there no leakage current in the ultracapacitor if you have such a small?
If you apply large enough voltage, you build up enough voltage, you do have leakage current. And this brings us a very exciting point. If you don't work on a supercapacitor, you don't appreciate a lot more, is leakage becomes such a painful issue to deal with in ultracapacitors. You need your electrolyte to be extremely pure. Your voltage needs to be controlled very well. Your material surface, what's the chemical functionality is so important. So that becomes one of the most important issues related to ultracapacitor.
Is there a physical separation at that junction, or is that just a non-reacting fact that there's no transfer of charge between the electrolyte and the metal?
Oh, they are in contact physically.
So why doesn't the electron just hop across to the?
Well, then there's a chemical reaction, thermodynamic driving force right there. You do need the voltage to be high enough. Once you can jump the electrons from one side to the other, you need to have chemical reaction happen. And then you look at the free energy, whether that can happen or not. You need to have high enough voltage. That's why this voltage is limited. You cannot take the V and go forever higher. And water is 1.23 watt. That's the limit. Yeah.
So you can't have any electrolyte. You'll have to have a special electrolyte.
This one, actually, water will do the work. Also, you just cannot apply. You cannot apply much higher than 1.23 watt. That's the thermodynamic voltage. Water will get split.
What if you have saline water? What if you had salt in the water?
You have salt in the water. That's what I'm talking about. It's similar as it's the water guiding the water thermodynamics guiding the principle. A battery is different now. These two use the surface to store charges. And battery is actually the whole piece of the electron materials. Electrons goes in deep inside. Ions go deep in. So at the end, the difference is capacitors and usually, to be exact, it's ultracapacitor right here. It's the surface storage mechanism. But the battery is a bulk storage. You store a lot more charges. Now you also see the difference. Why batteries power is lower compared to the capacitors and supercapacitors. When you apply a voltage between the two electrodes, electrons are moving. Electrons are very light, right? And so you can charge out these capacitors very fast. If you go to the ultracapacitors, you need to apply a voltage. Electrons are moving on these two pieces of metals, but you need ions. They need to move too, and the electrolyte. Ions are so much heavier. They move a lot slower. So the discharge time is longer. The power you get out is lower. But now you go to batteries. If these two electrodes, they are all solid. Ions need to move into a solid. That's a lot more slower compared to the ions only move in the liquid. In this case, ion needs to move in solid as well as in liquid. So it's harder to get high power. They move slower now. So you have a trade-off. The more you can store, the slower they move in the solid state, so you will get less power. Now you might want to think about, maybe I can design a breakthrough technology I can get all the things move so much faster. I'm going to get to that at the end. This crazy idea how to do that, this challenge as well.
Is that why there's that slope on the third slide with the supercapacitors between energy density and power density? That trade-off?
Yes, that's right. Go back to the slide. Yeah, it's right here. The power right here, capacitor is extremely high. Supercapacitors is lower, batteries is lower. Is that the slope you're mentioning? Yeah, that's right.
Are you doing any research on the solid state ultracapacitor?
I do.
Are you going to talk in the presentation to that?
I'm going to mention, yeah, at the end. I want everybody to get the principle to think about the supercap and the batteries first, to give you enough background in the future. Anything you see, you know how to think about that. Let's see. So at the end, how much energy you can store? Right? That's one so important parameter you care about. Come back to this chemical reaction delta G free energy. But this constraint right here, it's the weight of the materials you put in. So A and B produce AB, so the weight will be A plus B, the reactant weight. The amount of energy divided by weight give you specific energy. Now let's do a really simple estimation on the lithium ion battery used in the current technology. And some of you might not know when people talk about this parameter, what exactly do they mean? This is the reaction, carbon as a negative electrode. It's graphite carbon. We use carbon 6 right here, 6 atom to indicate that. You have lithium cobalt oxide. Now you put lithium into carbon, you charge out your batteries, produce lithium carbide, and lithium cobalt oxide now going from 1 to 0.5 lithium right here. Usually people don't go down more. If you go down more, lithium cobalt oxide is not stable. So this will be the limit. Now this free energy of change is 357 kilojoule per mole. And you calculate it, voltage will be 3.7 volt. And now you look at the weight, A and B, these materials, the weight add together per reaction. You have 1 mole of carbon 6, 2 mole of lithium cobalt oxide. You calculate it. This is the weight you put in. So we don't consider other dead weight electrolyte, metal current collector, etc. And this is for calculating what's the theoretical limit you can get right there. Every time people talk about a theoretical limit of energy, a density of specific energy, they refer to only the electron materials right there, no other dead component. You get this number, 370 watt-hour per kilogram. There's some unit exchange you need to do to get to that number. So that's the way to do it. Now let's come to look at this delta G a little bit. So we all know, everybody knows gasoline produces so much energy, right? The energy density is so high, giving a certain weight of gasoline. And you look at the delta G right here in terms of per mole. This is actually fairly high too, 357 kilojoule per mole. Gasoline probably get to maybe somewhere around 1,000. So, anybody know the exact number? Let's say if you burn the gasoline, is it probably 1,000 kilojoule per mole range? Not much higher than that, or it's probably around that. So you're not too far away in thinking about that. How much energy you can get out per mole of reactant. But the killing factor right here is all these guys are heavy. That's the weight, reactant weight. To really get the energy out due to the lithium ions going in and coming out, you need to add all these dead atoms, cobalt, oxygen. All these things add together is the weight. And then to make a battery, eventually you have current collector, you have electrolyte. All these things add together make the battery's specific energy or energy density much lower. It's 10 times or more, or 20 times below gasoline. But there's no reason, based on this fundamental reaction, you cannot boost that higher. You need to find a new type of chemical reactions and convert it into an electrochemical method to extract our energy. In the case of fuel cell, that's exactly the case, right? It's a hydrogen and oxygen react. You do an electrochemical method, that's fuel cells, you can get a pretty decent energy density. So watt hour is often used in the discussion of energy of batteries. It's not the international unit of kilojoule per gram, the standard. So now let's correlate back. We know this is energy you have. I give you only one equation I use in this tutorial. That's delta G equals minus NFE. This gives you the voltage. If you redo this a little bit, actually N times F, that's Q, that's the amount of charges you can store, and multiply the voltage. If this is divided up, this is actually the charge per unit weight of reactant. That will come to the idea, how do you look for materials to store more energy? We know to get more energy, you need large free energy delta G. You want the lightweight of materials. If you get these two, you will get it. You can look at this in another way. Looking at using this equation right here, you need high voltage. That at the end come back to related to higher delta G, right? High voltage, you need high specific charge storage capacity. In this case, it should be lightweight. It should store more charges per unit weight right here. That's this term. So if you look at lithium cobalt oxide, now this is the way, if you're not familiar with battery materials, how you get out how much charge you can store per unit weight. That's so-called specific charge storage capacity. Let's you look at these materials. You know you can get 1 mole of this material, you get 0.5 mole of electrons out, because we only use 0.5 of the lithium right here. You know the molecular weight of lithium cobalt oxide. You know 0.5 mole electron, and calculate how much charges for 0.5 mole. This is Faraday constant. At the end, it's 150 milliamp hour per gram also, roughly around there. So this is the term people use so often. Every time they talk about battery, how high the capacity is, they give you a number, milliamp hour per gram. It really comes from just molecular formula. That's how you get it. So now you know if you reduce the weight, you don't use heavy element right here, you do have the higher specific charge capacity. Now let me ask you, well, I mentioned to get a battery out, to get a voltage out of batteries, you need the 2 electrodes. They like the electrons in different degree, right? One like to keep electrons, one like to lose electrons, then you have a voltage. What's really the theoretical limit? How high the voltage a battery can go? Looking at all these material, different reactions, you might not be able to see it if you see it in the back. And lithium is the most electropositive element. That means lithium like to lose electrons the most. Now I ask you, what's the theoretical limit for the voltage in the batteries? That's right. It's just this one. Looking at the smallest, the most electropositive and most electronegative element, that's fluorine. That's great. We can get a 5.9, close to 6 volt batteries. Why don't we go ahead and do it? Certainly, fluorine is not fun, so that's the challenge. Otherwise, lithium fluorine battery will become popular. So also come back to the lightweight. If you look at periodic table, how do you get lightweight? That becomes so simple. You usually don't go beyond this box, right? Going beyond this box just means it's so heavy if you go down right here. And the elemental abundance is not high enough. It's within this box. The abundance in the earth is large enough. You really consider to use that as a batteries. You see certain battery technology phase out. One reason, not for all the reasons, just one possible reasons among all, can be it's not abundant, it's too heavy. It's not within this box. Now you look at the lithium-ion battery we use carbon, right? That's very lightweight. We use lithium cobalt oxide. Cobalt is right here. You would like to move to the front a little bit so you can reduce the weight a little bit. In the future, if you look for large-scale applications, it should be inside this box. Don't go beyond this box. Now let's look at lead-acid batteries. Question?
One quick question. So, as far as weight is concerned, you're really constrained to what you have on that box. But as far as the electro or the electro affinity differences were concerned, those you don't have an exhaustive list, right? I mean, so there's the possibility you could come up with some reaction or some combination of elements that has more affinity or less affinity, and so you could have more breakthroughs there?
Yes. In terms of electroaffinity, you play with the oxidation state of this element. You go to high oxidation state, they like to take electrons out, their voltage will be higher. You can also play with the combination of different elements to tune that electroaffinity slightly. That's true. And if you look at electroaffinity on this side of the periodic table, they like to give electrons away. So on this side, they would like to gain electrons. This will be the guiding principle for you to think about. And also one thing I like to mention, since periodic table is right here, you see we have fuel cell, we have proton-related technology, we have lithium-related technology. There's a reason right there why we choose these two. Others are so hard to work with. It's because proton is small, lithium is small, right? You want ions to move fast and solid. How do you do it? These ions need to be small. That's the first thing you need to think about. If you go down right here, that's too big, you go down right here. And if let's look at Mg, magnesium, if in a 2+ state, it's also very small too. Right? It's a 2 oxidation state, and it becomes a cation, it's very small. But unfortunately, magnesium is 2+ state. The electrostatic interaction with environment is too big. So magnesium moves so much slower compared to lithium. Lithium is only one charge. You need to have a lower charge, they move slower, faster. They don't interact with surrounding that strongly. So if you can come up with an idea to use magnesium, or even let's say aluminum, 3+ charge, that will be excellent. Your energy will go up a lot, right? Because the charge becomes more now, you will gain more energy. But the challenging is the one I mentioned. How do you get them to move? That's not easy. So looking at the lead-acid battery, that's really the working horse for a long time for the car. This is the reaction for the whole batteries. You have theoretically 2 watt of batteries, and coming back to the energy density, you can calculate. Lead is too heavy, atomic weight is 207. Cobalt in the lithium-ion battery is only 59 also. There's a big difference. At the end, it comes back to the energy density and specific energy. And the lead acid is right here in terms of energy per unit weight. And this is a lithium-ion battery, it's a lot higher. So it's a lot more attractive compared to other technology. Now let's focus on lithium-ion batteries and learn a little bit more about how batteries work. Question?
Yeah, just explaining the lead-acid batteries have been around for a long time to say a workhorse. So, what are the characteristics of lead-acid batteries that are so favorable? I guess it's worth thinking about why the standard is the standard.
I think we are lucky. We are very lucky. First of all, this uses hydrosulfuric acid. This is 2 watt. It's an aqueous solution. How do you get 2 watt out of it? Right? That's you need to be very lucky. So water gets split at 1.23 watt. There's something right there, a kinetic barrier to really hold on these batteries to be a high voltage. And it also happened to be this one is invented 150 years ago. It's the first rechargeable battery we ever invented. We probably put in a lot of resources and started this one. This reaction is reversible. And later we do have nickel cadmium, nickel metal hydride. They're also working very well, but this has a concern of cadmium that's toxic, so you don't want to use it anymore. Nickel metal hydride involving some rare element inside.
So
Yeah.
sodium sulfur rely on this
Sodium sulfur, I don't have the detailed number. Sodium sulfur should be, if you calculate the theoretical one, sodium sulfur is actually, I think it's somewhere probably around here. Yeah, it's high, on the high side. Now let's look at lithium-ion batteries. This is a basic structure of lithium-ion batteries. Now this comes to the real structure. You know, there's a lot of details inside to get it to every detail matters. This is the negative electrode side. This is positive electrode. Typically, you use a foil of metal. It's in the order of, say, 10 micron thick only. And then you put the carbon particles on the negative side onto this metal foil. This is copper. And this special requirement, why it's copper, it's not aluminum, because aluminum reacts with lithium in a low voltage. So what exactly is the foil you choose actually also matters. You put the particles down, and as we say, you need electron and ionic conduction in the electron materials right here. You need ionic conduction and electron insulation in the electrolyte. How do you do it? You want this particle to be conducting. You want them to in touch with each other strongly without detaching away. So you use a polymer binder on the surface, and then and get everything together. And you want them to be very conducting. You actually also add in the conducting additive, these tiny, very conducting particles to get everything together. Even though graphite carbon is already conducting, you still need that. On the other side, lithium cobalt oxide, you also add in these particles. And to make it conducting, you add in carbon. You know, you add in this binder also. You need to press them very tight so they are in close contact. They can be conducting. You need a separator to separate these two electrodes to prevent shorting. And this separator also needs to let the ions, lithium ion, moving through, so you can put in the liquid electrolyte inside. So at the end, this is ionically conducting component. And the electrode, since you need the lithium to go into the structure of the materials, they needs to be both electronically and ionically conducting. And then after you have that, you roll this up into this jelly roll. This is the typical form factors we use. This is cylinder cell that show up like this at the end. Well, when you look at the structure, you see all these jelly roll actually roll up together very tight to save the space, so you can increase the energy per unit volume. It's very important because this metal current collector, they're so close to each other. This is about, give you a length scale, about 50 micron. This is 50 micron. This is somewhere between 10 to 20 micron also. And you need to roll it in a way almost perfect. If there's anything, the metallic foil getting close to each other, there's a particle that's right there and go into your batteries, it probably will cause a defect and catch fire later. And we'll look at that a little bit more when we talk about, say more about the safety. So at the end, there's so many components involved. There's another component I'm going to mention in the next slide. That's additive. There's a lot of secret additive in the battery industry. You know, what chemicals I put in to stabilize my battery. I'm going to show you in the next slide why the additive is important. For all these components, you know, what's the ratio you add in? There's a detailed chemistry involved to really make battery better. Certainly many secret information you don't see. That's why battery is considered as a black art. It's more a science. It's a black art. There's so many components inside. They all interplay. Let me mention a battery separator right here. You don't see people talk about this too often. It's a highly porous structure. This is a nanoscale pores. A lot of liquid to move through. But once you make the battery, you compress the positive and negative electrode. You don't want them to short. So this separator, typically made of polymer, needs to be very strong, very well made. You cannot have a bigger hole like this right here. If you have that, you will have shorting. It's extremely important. LG Chem, a company in Korea, they developed a new type of separators simply just by putting a ceramic coating, it's hard inorganic coating onto this organic polymer separator. You can increase the safety dramatically for the mechanical strength reason. There's a lot of invention in that areas. So to talk about battery, let me mention this. You need to know about this, how people really evaluate the batteries. Once you have a battery, you need to charge it out and discharge it. The way to do it, you put a constant current. And the higher the current, the faster you will be able to charge out your batteries. And then you monitor the voltage over time. And what does that get you? You can produce this profile, voltage versus capacity. If you monitor the time, you know the current times time. That's how many charges you put in or take out. So you can produce this battery charge discharge curve voltage versus capacity and milliamp hour per gram unit. People use this very often, C-rate. What does it mean, right? How fast you charge and discharge your batteries. You say, if I use 1 hour to charge and discharge your battery, you call this is 1C. If you use 2 hours to do it, it's C over 2. But if you use half an hour, it will be 2C. So put this 2 in front of C, that's faster speed, and put the 2 behind C, that's slower speed. That's just the convention. If it's a C over 3, that will be 3 hours. Typically, for the portable electronics, when you evaluate a battery, you are doing somewhere, let's say C over 2, C over 3 also. That's the roughly the right time scale. If you do the car batteries, you need to go a lot faster to get more power out. Question?
Can you explain this chart? I don't understand how you're changing capacity. Is that just versus time and you're putting a constant current in it, or what is it?
You put a constant current into a battery to charge it up. It goes this way, the battery voltage stay as a constant and then go up. The reason it stays as a constant is this battery, lithium iron phosphate, measured with lithium. The free energy is a constant during the charge and discharge. That gives you the voltage, that's also a constant. And for the fact this voltage is very flat, this tells you it's actually lithium going in, speed is very fast. That doesn't prevent any kinetic barrier right there. It's a very flat voltage.
And why is like some of the curves are going up and there's one curve going down? What's that?
One is charge, you go up. And once you discharge, you also start from this side. When you finish discharge, the voltage will drop.
So is the final stage sort of more like a capacitive charge? Is that basically?
The final stage is you use all the iron phosphate now, all become lithium iron phosphate. And you want to put more lithium ions in. You know, it cannot hold more lithium ions. The voltage will jump out. It's like you're putting the charges onto electrode, almost like a capacitor. It will shoot out very high because there's no ions to balance the electrons. It will shoot out very high. Now let's look at the detailed process of lithium-ion battery. It is this chart to tell you there's many components of a battery you can do invention on. Let me show you this is a charging process for lithium cobalt oxide for batteries. Question?
Go back to the last slide. I understand the chemical reaction is reversible. Can we assume the charge and discharge rates are the same? Is there a way to control that?
Charge and discharge rate?
Yeah, just to have different rates, because I guess there are...
It's the current you put in, the current density you put in. You know the weight of the this material you have, how big the current is will control the charge and discharge rate.
Right. Is it possible to have applications where we want to charge fast but discharge slowly, or vice versa? So we want to control different rates.
Yes, and charge and discharge rate can be operated in different rate. Unfortunately, usually, you can discharge your battery, use the energy very fast, but it's much harder to charge it very fast. That's actually what you want, to charge it very fast for the electrical vehicles. For one of the reasons is the safety. Let me come to this slide, why something bad can happen if you do the fast charging. So during the charging process, let's look at what will happen. Right? You have a battery, you measure the carbon potential versus a reference, that's your lithium metal. You also measure the lithium cobalt oxide. Now you start to put in current, you monitor the voltage to see what happens. Let's look at the negative electrolyte first, that's a carbon. Once you put lithium into carbon, and the potential drop in the carbon, that's the negative side. And then you put, it's going below roughly around 1 watt, somewhere around there. This side chemical reaction happen. You use organic electrolyte. We know once you get a potential of a material lower, it's so reactive. You look at lithium metals, you put lithium metal in contact with most of the materials in the world, lithium is going to react because lithium likes to give electrons away. Once you put the potential lower, this electron will like to give electrons away to the solvent and the battery electrolyte. You start to build a film or passivation film right there. You need this film to build very nicely. And it took so many years for the battery industry to really know how to build a nice film. At the end, you want this film to self-passivate it. You don't want the electrons from the negative electrode to go onto the organic molecules anymore. You don't want that. And you want this film to be ionically conducting. Lithium can still come in from the electrolyte, but it's electrically insulating, so electron cannot transfer from the electrode to the electrolyte solvent to stop the side chemical reaction. If you keep having side chemical reaction, you consume your electrolyte and you consume your lithium. At the end, the battery is dead. That turned out to be very important. Now when you get down and this voltage, you get more and more lithium going to carbon, right? If you put more and more lithium in, let's say you hit to this dashed line right here. That's the 0 watt versus lithium metal, and that voltage, you start to have lithium metal deposition, electroplating onto carbon, start to form lithium dendrite. And once you deposit a metallic structure, metallic structure grow in a filament manner. It shorts your battery, it catch fire, it causes explosion. So you need to control your charging voltage, not go over to the degree you have lithium metal deposition. Now come to the fast charging. How do you do fast charging? You drive a lot of current through it, and you have over potential. You have a kinetic process that they cannot react so fast. And then what the batteries do, the charger do is you just put in higher and higher voltage, right, to drive current you like. At the end, when you put in more voltage, this carbon electrode can go below the lithium metal deposition, electroplating potential. You're going to play out lithium, and then battery explode. The other side, lithium cobalt oxide, during the charging process, you take lithium out and put it into carbon. This becomes less and less lithium. The potential goes higher and higher. But this limit right here, around 4.3 watts also, above that, you start to oxidize the organic electrolyte in your batteries. And once you have oxidation reaction happen, we know that's an energy generation reaction. And your battery heats up. And once it heats up, to about 250 degrees C also, for lithium cobalt oxide, it's not stable anymore. It starts to release oxygen. Keep giving out oxygen. Now you have more oxygen coming out. It's going to oxidize more of this organic solvent, release more heat. Now it just accelerated. It's going to explode the batteries. So also means don't overcharge your batteries. If you overcharge, the positive side can go too high. the battery also explode. So at the end, it's really a delicate balance. How do you really control all this process going on, possibly happening in the battery to make sure it's safe? And also, this also related to how many cycles you can do your batteries, charge and discharge, and how do you control this side chemical reaction? Question?
The passive film that forms, like Juan, you already said this, is building up at what point in the battery? Is it building up at the current collector interface?
This is passivation film is on the surface of each of these particles. Yes. There should be some also on this surface too, because when you get the potential low enough on copper surface, the electrons can also transfer to the solvent. So you also have something right there. But the main concern is on this particle surface. The surface area is a lot bigger on this particle.
And what you showed on the chart indicates that even though this film builds up pretty early in the charging process, it doesn't preclude the continuation of charging out to about X equals.
It doesn't, because lithium ion can still come in. That's what you need. And this film you form and this potential is a lithium compound, lithium organic compound, lithium carbonate, lithium fluoride, and lithium ion can still go in, but prevent the electrons to go across. So
on the previous slide, the potentials that you are concerned with for safety purposes are potentials relative to the electrolyte potential, right?
Right.
And the breakage happens at different points
Right.
as far as the total potential. So for battery safety purposes, do you have to actually be measuring that internal electrolyte to cathode and
You mean the measuring against the lithium reference? For 2 decades now, right? And people don't do that because this requires 3 electrodes inside the batteries. And the engineering design is so much more challenged. The cost is so much higher. People don't do that. At the end, how do you control the voltage? You need to balance how much material you put into positive and negative electrode. You calculate that exactly. And you do the testing. In a certain materials balance, certain ratios, you always control the voltage within certain range. Don't go over to the dangerous potential. A lot of experience built inside those controls. Usually in academia, we cannot do as good job as industry. They spend years and years to learn about this. Now we start saying they also recognize you cannot control this potential so well during your manufacturing process. There's always a weight variation. Even industry start to think about maybe I should put in a tiny piece of reference electrode into my batteries. So I monitor both electrodes' potential exactly. My electronics, power electronics will know when to stop. That's much safer. I think that might be the way to go, to really know exact potential for each electrode inside the batteries. Now coming to all these parameters, specific energy, specific power, we define cycle life, and we know 300 cycles you need for electronics, 3,000 for the cars. And one thing, let me add in right here, Coulomb efficiency. That's when you charge out your battery. Let's say you put 1,000 electrons in, 1,000 lithiums in, ions in. How many can you take out? Why that is important? Because if you need to go to the car batteries to have application, you need 3,000 cycles. Each time you lose 1 electron, that often means you lose 1 lithium ions too. There's a side chemical reaction. You need 99.99% of Coulomb efficiency. After 3,000 cycles, you only have 74% of the initial capacity, the energy remaining. So this is not trivial. How do you get 99.99? Looks like just a purely engineering problem. No, it's not purely engineering. There's a lot of science issue you need to address. And every single step of a reaction, you need it to happen almost perfect. You don't lose any single lithium ions. So it's really highly engineered device system to get to that. So let me mention a little bit more about safety. How does the safety concern, how do you get the battery explosion happen? One reason is the lithium dendrite formation. Once you go to low voltage, you deposit lithium metal out, and it's going to grow from positive to the negative side, and then short your batteries. Once you have shorting, that generates heat, and heat up the batteries. Now lithium cobalt oxide can start to release oxygen, come back to oxidize the electrolyte. So it's going to explode. And also in the manufacturing defect, you see in the batteries, a manufacturing room is actually a clean room, right? Not only semiconductor industry use clean room, battery manufacturing use that too, to reduce the dust. If you have a big dust sitting right here, you make your battery, you compress, and then it's going to cause a hole formation in your separator. Over time, that's the part slowly heat up, and that's the part start to produce problem. And I heard Sony has that big recall. A rumor said that's the manufacturing defect due to the metallic foil right there they use, and it can produce that metallic dust, and eventually cause shorting. Question?
You mentioned that you could lose electron or lithium. Are you losing it through like reduction of lithium into metal form? Is that how you're losing it?
No, if you lose it, most likely in a way, and you have organic electrolyte inside the batteries, they like to react with very reactive or negative electrodes. They also like to react if the positive electrode voltage is high, they get oxidized. From a lithium compound, you lose the lithium and form of a lithium compound formation on the surface of the electrodes. So, well, let's see. Time is running out. I do have other slides to show, but this is the purpose to get you to ask questions. Even though I don't get to the end, that's fine. But let me come to the end of the last slide to mention a little bit of what I think. When you look at the batteries, you need to first of all really stand very high, 1,000 miles high, and look at the big pictures. Why you do certain things? You choose certain materials to make batteries. What are the challenges you are trying to address? First of all, batteries, the electrolyte can be solid, liquid, and gas. Let's look at different technologies. Lithium ion, we have negative electrode, that's carbon. Positive is lithium cobalt oxide, it's a liquid electrolyte. It's a solid, liquid, and solid. Why do you do that? And why not just use all solid? The reason is lithium ions move so much slower and solid. So you actually would like to use liquid component as much as you can to increase the lithium diffusion rate so you can have high power. And another way is sodium sulfur batteries, right? Try to use more liquid now. But liquid really going into the negative electrode and positive electrode above 350 C, they are in the molten state. They move so much faster, you increase the kinetics. But you have to use solid electrolyte, because if you put 3 liquids together, it's so easy to mix them out and cause shorting. So the rule of thumb is you need to have at least one solid component. Batteries have at least one liquid component. But for the thin film battery, you can put on a computer chip, right? You don't want the liquid to go everywhere. It's actually all solid state batteries. You can control where the materials is. They don't go everywhere. Recently, you heard about this in MIT, right? There's a professor in material science saying, well, we know lithium can move so much faster, and liquid, why not we all use liquid? So he's trying to use now is above 700 degrees C, using the molten state battery. It's a molten liquid metal for the negative, and it's a molten liquid for the positive electrode. Now the electrolyte is also molten. Now you have 3 layers, bottom layer, middle layer, and the top layers. And then this type of batteries can be very good for large scale energy storage, because ions can move so fast. You just put the liquid in, but you have to understand the challenge of why it didn't happen yet until recently. It's because it's so hard to deal with all liquid phase. You can mix them up so easily. There's atomic species migration to cause self-discharge, and the high temperature. There's a lot of material science issues, like chemical reaction happen. But this does represent from the high level, what's the thinking behind. And let's look at lithium air, right? This is an example I want to give it to you, is electron can be solid, can be also gas. If this gas comes from the air, that's the best. You get it for free. You don't need to carry the air all around. You basically, all the air mass is just from the air. You carry the positive electron and negative electron and carbon collector to interact with oxygen. So lithium ion batteries do have the energy density as high as close to gasoline. This chemical reaction, lithium and oxygen react, produce a lot of energy. Oxygen come from the air, it's free. So there will be a lot of thinking behind this now, and now you think about battery for different applications. What exactly do you need? For portable electronics, for the electrical vehicle, for large scale energy storage, it's different. And certain state of metals right here really fits in very well in certain applications, but not the other. It's now also the time to go back to the chemistry and find the right chemical reaction you can use, produce high free energy, having the right kinetics to make new type of batteries for the different application. Thank you for your attention.
For more, please visit us at stanford.edu.